Hi, today we are going to study about approximating the sum of an alternating series by Sn. This is the error estimate in approximating an alternating series. Suppose sigma n equal to 1 to infinity minus 1 raised to n minus 1 an. It's an alternating series. So error estimate in approximating an alternating series means approximating means suppose sigma n is convergent so that it has a sum s. If Sn is a sequence of partial sums, then limit s minus Sn is equal to 0 actually. And then actually this s എന്ന് പറയുന്നത് അതിൻ്റെ ലിമിറ്റുമാണ് എസ് എന്ന് പറയുന്നത് സീക്വൻസ് ഓഫ് പാർഷ്യൽ സം ആയിരിക്കും. അപ്പോൾ അതിൻ്റെ ഡിഫറൻസ് ഉണ്ടാവും. ഓക്കെ, അതായിരിക്കും നമ്മുടെ റിമൈൻഡർ ആഫ്റ്റർ n ടേംസ് വരും 6, റൈറ്റ്. അപ്പോൾ ആ റിമൈൻഡറിന് അനുസരിച്ചിട്ട് നമ്മൾക്ക് എറർ ഫിക്സ് ചെയ്യാൻ പറ്റും നമ്മൾക്ക്. ദാറ്റ് ഈസ് എറർ എസ്റ്റിമേറ്റ് ഇൻ അപ്രോക്സിമേറ്റിംഗ് ആൻഡ് ആൾട്ടർനേറ്റിംഗ് സീരീസ്. Suppose these satisfy these two conditions, and if S is the alternating series, then mod Rn is equal to mod S minus Sn, which is always less than or equal to An plus 1, which is always less than or equal to An plus 1. In other words, the absolute value of the error incurred in approximating S by Sn is no larger than An plus 1. The first term omitted. An plus 1 ആയിരിക്കുന്നതിനേക്കാളും ലെസ് ദാൻ ആയിരിക്കും അതിൻ്റെ ഡിഫറൻസ് വരിക. Look at the proof. S minus Sn choose ചെയ്യുക. S അറിയാം, k equal to 1 to infinity minus 1 raised to k minus 1 ak minus sigma k equal to 1 to 1, that is Sn minus 1 raised to k minus 1 ak, that's equal to sigma k equal to 1 n plus 1 to infinity minus 1 raised to k minus 1 ak, which is equal to minus 1 raised to n an plus 1 plus minus 1 raised to n plus 1 an plus 2 plus etc. Taking minus 1 raised to n outside into an plus 1 minus an plus 2 etc. Let's say an plus 1 a minus an plus 2 etc. By combining the first two terms and second and fourth terms etc., we can say that this an plus 1 is less than or equal to an for all n from the assumption. So an plus 1 minus an plus 2 is always greater than 0. Each term is greater than 0. Each pair term is greater than 0. So an plus 1 is plus 1 etc. are greater than or equal to 0. So mod S minus Sn is equal to, which is positive. Every expression is positive, so it is always that is an plus 1 in the decrease in our term. So mod S minus Sn is always less than or equal to an plus 1. And this is the proof. Okay. To prove that sigma minus 1 raised to n 1 by n factorial is convergent, find its sum correct to 3 decimal places. N plus 1 is equal to 1 by n plus 1 factorial is equal to 1 by n factorial into n plus 1, which is less than 1 by n factorial, which is equal to an. For all n, limit n tends to infinity, an equal to limit n tends to infinity 1 by n factorial, which is equal to 0. Next is mod Rn is equal to mod S minus Sn, which is less than or equal to mod an plus 1, which is equal to 1 by n plus 1 factorial. Mod Rn is less than suppose that we have to record that R must be less than mode 0.0005, or that is greater than n plus 1 factorial greater than 2000. So after calculating, we will get a n is equal to 6. Okay. We have to do these exercises also. These exercises you have to do. Next, we will study about the absolute convergence and absolute convergence, the ratio, and the root test. Absolute convergence series means absolute means the modulus sign actually. Okay, so absolute convergence means if the series mod sigma mod an is convergent, then we should say that sigma an is absolutely convergent. Sigma an is absolutely convergent. We have to show that the series is absolutely convergent. Okay. The series is absolutely convergent. Taking the absolute value, and it will become 1 by n square. This is of the form 1 by n raised to p, with p equal to 2, which is greater than 1. So this series converges. Okay, so this series is absolutely convergent. Next is minus 1 raised to n minus 1 by n. This is alternating series. We have to check whether it is absolutely convergent or not. So taking the modulus, then this will become 1 by n. 1 by n is, this is actually divergent. Okay, so this one is divergent. It's a divergent harmonic series. Conditionally convergent series. Conditionally convergent series. If sigma an is conditionally convergent, if it is convergent but not absolutely convergent. Absolutely convergent series are always convergent, but absolutely convergent means convergent, but convergent will not imply absolutely convergent. So it is conditionally convergent means if it is convergent and not absolutely convergent. Theorem 1. Sigma an is absolutely convergent, then it is convergent. You have to prove this carefully. Okay. So next theorems and the problems we can do in the next video. Okay.